Chapter 13, last chapter in Organic Chemistry 1. Talks about radical reactions, so we first need to know what a radical is. You remember when we have homolytic breakage of the bond, we will end up having radicals. You should be able to remember this process. When we use hooks instead of arrows, and each of the electrons involved in the covalent bond remain on one of the atoms, so the atoms remain with one single electron. They are called radicals, which are very active. So that's how radicals form. As far as the stability of radicals, they're exactly same as carbocations. So if the single electron remains on a carbon connected to 3 hydrogens, it's going to be the least stable. Then by increasing the substituents, by increasing the number of carbons on the carbon of radical, the stability increases. So the primary is less stable than tertiary, tertiary less stable than, secondary less stable than tertiary. So primary, secondary, tertiary, and this radical, methylene radical, is going to be the least stable. Okay, so what we learn, the first one is halogenation of alkanes. If you remember so far, we did not talk about any reactions of alkanes except their combustion. But one very rare reaction that can have for alkanes is to force them to exchange one of their hydrogens with a halogen. So what happens? You definitely need UV light or heat at the catalyst, because why it's difficult to force the alkanes to react? Because they all have single bonds, they're fully saturated, and they do not want to react. So you need to know the steps of halogenation of alkanes and what happens in each. So the names of the steps and what happens in each. The first step is called initiation step. You need a halogen because you are going to force the alkane to accept the halogen. So you have a halogen molecule, you use H nu is for UV light. That's the symbol for UV light, correct? Or you use heat. Delta is the symbol for heat. So what happens? A homolytic breaking of the bond happens. Don't forget to use the hooks, not the arrows. Hook means half of the electrons transfer to each one. So the first one in the initiation step, you will have 2 radicals. You created 2 radicals of chlorine. In the second step, which is called propagation, the reaction starts propagating. Let's say we have this alkane. We are going to add or replace a hydrogen of this cyclopentane with a chlorine. So cyclopentane. Your alkane can be cycloalkane or just a regular alkane, doesn't matter. Plus one of the chlorine radicals that was produced in the previous step. So what does this radical need? Just one single electron, right? So hydrogen will put a share of 1 electron, and 1 electron will remain on what is left from alkane. So we will end up having a radical here, a new radical, right? And of course HCl here. Then, if you call it the first step, this is going to be the second step, then we will have more than one chlorine molecule. So we will have the reaction between chlorine molecule and this new radical. Now the radical needs one more electron again. So one of the chlorines will put an electron with this radical and a new radical will form. This is your chlorocyclopentane, which is going to be your product, main product, major product, okay? What else? Now we have a new radical, correct? So, this was the propagation step. At the termination step, when the reaction is about to stop, you have different products formed. You have different chlorine radicals formed. So you have a chlorine radical from here, you have a chlorine radical here. So you will end up having, this is going to be called step 4A. Let's call it 4A. So you have the formation of chlorine molecules again. You see, this feeds the reaction again. You will end up having, you still have not all the radicals of cyclopentane will react with chlorine, so you still have them in the system. So two of them will react to form a new radical, right? This is going to be reaction 4B. These are the possibilities for all of these reactions. Or you can still have more. One of these radicals, they will form. So whatever is left over is, you will have them reacting with each other at the end in the termination step. It's a very difficult reaction to happen. You definitely need to apply heat or UV light, and you will end up having different products, but the major product is what is formed in the propagation step. Okay, so these are the three main steps: initiation, propagation, and termination. The major product will be formed in the propagation step. The minor products, the byproducts, will be forming in the termination step. Okay, make sure you learn it well. So far alkanes just underwent the halogenation, and we have combustion when you burn them in oxygen, just like what you do in the stove or oven. You just mix propane with oxygen to produce heat for you to be able to cook. Alkane halogenation can form different products. We just worked on monohalogenation, just replace one of the hydrogens with halogen. But we can have monohalogenated, right? One of the hydrogens is replaced by chlorine. If you have enough chlorine and you let the reaction enough time, more hydrogens will be replaced by chlorine. So at the end you have all of the 4 hydrogens replaced by chlorine. In the case of methane, it's very simple, but what if you have a molecule like butane? A molecule like butane, we have to pay attention to the type of the hydrogens, because we are going to replace these hydrogens. The hydrogens attached to primary carbon, they are all primary hydrogens, right? The hydrogens attached to secondary carbons, are secondary hydrogens. So depending on which of these hydrogens is replaced, the type of compound is different. How many primary hydrogens do you see here? 3 and 3. 6 primary hydrogens. And how many secondary? You see 2 plus 2, 4. So the chance of having these 6 hydrogens, primary hydrogens, to be replaced is more chance, right? 6 versus 4. But which one is more stable? Because secondary hydrogens, when they are replaced, they will form secondary radical, and then they are more stable. So we will end up having either one of these primary hydrogens to be replaced. We're just considering the monohydrogenation, halogenation. 1 chlorobutane. The studies show that 30% of reaction of the product is 1 chlorobutane, and if one of these secondary hydrogens is replaced by chlorine, then you will have 2 chlorobutane. So almost 70% is this product. So you see, although you have more chance for primary hydrogens, but only 30% is 1 chlorobutane, but 70% is the more stable product. You can use it for any other reactions. If there is any difference between the hydrogens, you need to be careful to make sure you have the mixture of products and determine the major product on each. All right. It can be different, this percentage can be different for different molecules. It's not necessarily always the same ratio. Okay, for chlorination, you just saw we have different products. Another molecule can be this. So you just saw we have, these are all primary. You have an example in the book. And this is a tertiary. So you can have one of these primary hydrogens replaced. We're talking about monochlorination, okay? But we also can have this hydrogen be replaced. Which we have the mixture, and the studies show that this one is 65%. How many primary hydrogens do you have? Primary hydrogen, you have 9 here, 3, 33. And tertiary hydrogen, you have only 1. So in this case, because the number of primary and second and tertiary hydrogens are not even close to each other, you have many more primary hydrogens. So the chance of chlorination in primary hydrogen is more than tertiary, although tertiary is more stable, but you have more percentage of what you have more. But the case for bromination is more selective. More selective. So means that if you have bromine, so you will just have this compound. So if you're aiming to have the more stable only, most of the product this, and you will use bromine. If you don't mind having the mixture of products, you can also use chlorine. As far as the stereochemistry, if you have a stereogenic center, then your product will form a racemic mixture. So we have the mixture of products, but if you have R or S, you will have the mixture of R and S. So let's see, we are going to replace one of the hydrogens in one isopropyl, one methyl cyclohexane with bromine. Right? We have these hydrogens, secondary, or this carbon does not have any hydrogens, and this carbon is tertiary. So which one is going to be the major product? Secondary, and secondary. These are primary, and this is quaternary. We don't have any hydrogen. So which one will be the major product? The one that is formed from more stable radical. So you have a bromine here. Okay? And rest of this chapter we will work on allylic bromination, and here it is. Allylic bromination. In the allylic bromination, you have, again, this is the allylic position, allylic carbon. Do you remember we said allylic carbon is the one next to the carbon of double bond? So this is the allylic carbon, the one next to the double bond. So if you have a radical, what you have here is the resonance. So for allylic bromination, you have the possibility of resonance. This is allyl radical. It's extremely important to know what is an allylic position or allylic carbon, and then we can work on this. So if we want to draw the resonance structure of, for example, this, then one of the electrons of double bond and this electron drawing the hooks Then drawing the resonance arrow, it shows that as if like double bond is moving between the two adjacent positions. And don't forget to leave a radical here. So that's how it forms. If we want to work on another one, this carbon is too far from here. These two carbons, carbon of double bond and the radical. This is the allylic position, allylic carbon. So this double bond can share one electron with this to move double bond to the two next carbons. There is an electron left here because we are moving only one of them. And double bond forms and nothing happens to the other double bond. And a good source of bromine to do the allylic bromination is, do you remember NBS? We had it in alkenes also, NBS and bromosuccinamide. We said B stands for bromine, is a good source of bromine. In the presence of UV light or peroxide, UV or peroxide, we have to have some extreme conditions. So where is the allylic position? It's either here or here, right? We want to put bromine. These are the carbons of double bond. In this case, they are the same. So we can put bromine here without touching the double bond. So what we gain in allylic halogenation or bromination is that we keep double bond at its own place. We just put a bromine atom next to it. So in the next part, we will go over the mechanism for this allylic bromination, and here it is, mechanism for allylic bromination. Mechanism. The same 3 steps. Let's say this is the initiation. So first, in bromosuccinamide, it's time to know the structure. This is NBS, 2 oxygens and NBr. So one of the electrons and one of the electrons of bond between nitrogen and bromine will remain on each of them. So we have the first radical formed. We needed the bromine radical, which is formed. In the propagation, let's say we have this alkene, and the alkene must have allylic position with a hydrogen available, right? So bromine is going to react. So you will create a new radical. HBr is the second product, and then with a bromine molecule that you have enough of them available, then you will have, because this radical needs only 1 bromine. So you will put bromine in the allylic position without touching double bond plus bromine radical again. And at the termination step, finally, you have different products formed depending on what is left in the system. Okay, so we can have this compound, or you can have two bromine radicals to form Br2 and feed the reaction. So that's the allylic bromination. I will work on a couple of examples, and okay, I will work on allylic bromination of this compound. Where is the allylic situation? Allylic carbon next to it here. So with bromine, if you add just bromine, that's what happens without light or anything. You will add, remember, you had bromination, you add bromine to double bond. This is, excuse me, what you learned in alkene chapter. But if you use NBS and HNO that we know, this is a recipe for allylic bromination. So you will end up having preserved double bond, and you have bromine. Okay, that's what you have. And also, if you want to work on another example, this is a good example. Again, with only bromine, you will be adding bromine to your double bond. Just a regular bromination, and you saturate your double bond. If you use NBS in HNO, you don't touch double bond. Allylic positions are either here or here. But the good point about this example is that you don't have any hydrogens to replace. So the only choice is here. You have to be careful. You must have an allylic hydrogen in the allylic position. So you will have this. Okay, in the remaining of this chapter, we will work on radical addition of hydrogen halide to double bonds and some more extra reactions.